Hello, this is the first video of the Polar Coordinates series for OCR Pure Core Further Mathematics and introduces polar coordinates. You will have used Cartesian coordinates for some years. These fixed positions of points in space using a grid of x, y coordinates. For example here, if we were to mark the point 3, 2. So this is 3 across on the x-axis and 2 up on the y-axis. But there are other systems to fix a point in the plane. If you think of radar screens used by air traffic controllers or rangefinders used by the military, the idea of an angle from a given direction and a distance from you is another system of fixing position. So polar coordinates use a distance from a fixed point, an angle from a fixed line, to locate the same points P. So doing that to get to that same point 3, 2, you would have a system where you have a distance r and an angle from the x-axis theta. Those polar coordinates would then be r theta as opposed to the xy for the Cartesian. The grid for polar coordinates thus looks more like a dartboard. The point 0 is known as the pole. In other words, it's the centre. And OX, the x-axis, is called the initial line and denoted as L. So the point P has polar coordinates r theta as shown, where r is the distance from the pole and theta is the anti-clockwise angle from L. Note that theta is measured in radians usually. For some curves or functions, polar coordinates prove to be more useful than Cartesian coordinates. If we wanted to write this point here, P, in terms of r and theta, on the grid we can count out 1, 2, 3, 4, 5 in terms of the rings, so r is 5. And we can see that in this particular grid, pi by 2 is 3 divisions of angle, and therefore in this case theta is 2 pi by 6 or pi by 3. And thus we would write P as being 5 and pi by 3 in terms of polar coordinates r theta. So let's try plotting these points on this grid, which, unlike the squares on an xy or Cartesian grid, shows circles of increasing radius and lines to show increasing angle. The scale, of course, will depend on whoever's drawing the grid. So if we were to look for 3 pi by 2, doesn't matter which you work out first, but the angle pi by 2 obviously is going to be a vertical line, and then we would count up 1, 2, 3 points. If we were to draw r in, then that r would be up straight line up there to give us that 3 pi by 2 point. Again, if we were to do the angle 5 pi by 6, given that these lines show divisions of pi by 6, we would do 3, 4, 5 and then count out 1, 2, 3, 4 to give us that point there. We don't have to draw the radius to the point. We could just leave it as the 4, 5 pi by 6 there. For the 2 minus pi by 3, you can see that in this case the angle is negative, so we would go in a clockwise direction, and that would give us this point here. If we were to find that r in a calculation ever proved to be less than 0, then we can consider this to be the same as a situation where the radius is greater than 0 but theta is less than 0. Each set of coordinates r theta defines a unique point on the plane. However, it's important to note that if we were to plot r and then theta plus 2k pi, where k is a constant, you would in effect have gone around a circle and back again. So say we had a point there and then we wanted that same theta plus 2 pi, we would have in effect gone around the circle and ended up plotting the same point again. Thus there is an infinite number of ways of writing P. If we do want a unique definition for the point P, we would use what we call the principal polar coordinates. Here r is greater than 0 and theta lies between minus pi and less than or equal to pi. Note the similarity with the convention used for complex numbers in modulus argument form. In the next video, we will see how to sketch curves with polar coordinate equations.